Hello and welcome back to Deploying Microservices with Puppet and Containers. I'm Brandon and I'm going to be giving you an overview of Puppet architectures and a short discussion on our target use case for this lesson, the creation of Docker images with Puppet. Alright, so the first and most common architecture is the Puppet Master Agent architecture. It's promoted as the default infrastructure by Puppet Labs. In fact, the Puppet Enterprise stack, as opposed to the open source product, is inherently a master agent architecture. So in this architecture, the Puppet Master compiles catalogs for all of the agents. The desired resource state is determined, all manifest functions are executed on the server, and the catalog is compiled and made available to agent nodes. And the Puppet agent will then apply the Puppet Master provided compiled catalog. On the right, we see a common architecture diagram. We see multiple Puppet agent nodes with two load balanced Puppet Masters. This is a common way to address scalability and redundancy, reliability in a typical data center environment. We also see a dedicated CA server and a dedicated Puppet DB server. In this particular setup, Puppet configuration is housed in an R10K configuration repository. R10K is a utility that allows for the aggregation and installation of Puppet modules from a multitude of different sources potentially. It also provides an elegant way to manage environment-specific module sets. One advantage of this architecture is it provides centralized reporting and inventory. Agent reports are automatically aggregated at the Puppet Master in this architecture. This simplifies report handler integrations as those integrations happen at a single point, the Puppet Master, as opposed to across all the individual nodes. PuppetDB can be used in these masterless configurations as well, but the configuration is a bit more complex as it has to be configured on all of the managed nodes. In a masterful environment as described here, this configuration only exists on the master nodes. One concern this architecture addresses is configuration management drift. In this setup, there's a certain inherent assurance that configuration will be consistent in that it's coming from a single source, in this case, the Puppet Master. Agents do not have to have knowledge of the configuration of other agents in this scenario either. There's a natural data protection and separation paradigm. Masterless setups often have the same configuration or module set on all of the managed nodes. A single source for configuration may make updates of configuration a bit easier as well. This data protection is an inherent benefit of this particular architecture. It's also it's a tried and true model. It's most endorsed by Puppet Labs. When people think about Puppet and how it's configured, this is what they think of for the most part. There's much more thorough documentation and support for this model. While a master agent architecture does require at least one dedicated Puppet Master, catalog compilation on the master saves resources on the target nodes. So, all the overhead associated with catalog compilation is taken by the master as opposed to on the individual nodes. If a catalog is applied and compiled on the agent, those valuable resources are going to be used there. The negatives about this architecture, there's quite a bit of setup involved, and there's use cases, and the use case described in this particular lesson, we may not see much of a gain from all of this architecture here. It requires a dedicated master or multiple masters as described in the diagram in this particular architecture. All the accompanying components, PuppetDB, the CA server, etc. It also, in an ongoing persistent management paradigm, you're going to have a strong dependence on a consistent, reliable network connection to all your nodes. So in contrast to the typical architecture, the Puppet Master Agent architecture, we have the Puppet Standalone architecture. No Puppet Master setup is required in a standalone architecture. It's executed through a simple Puppet apply execution on the node that is intended to be configured. You can configure common components like PuppetDB and Hyra. In this model, you can take advantage of those technologies, but it must be done on all the nodes. So you have to configure each individual node for PuppetDB You have to have a puppetdb.conf on all nodes. You have to have, if you're using Hyra, you have to have a Hyra.yaml on all the nodes. In a master setup, a master-based setup, you would only be configuring those on the master. R10K can also be utilized, and in this scenario, we will actually be leveraging R10K in the demonstration and the upcoming videos. On the right, you'll see some common invocations of Puppet Apply. The first one there, the Puppet Apply-E, you can execute any actual, parsable Puppet code, any valid Puppet code you can execute with that syntax. Something like in this example shown, include class would be a common use for this syntax. Although it is also possible to apply more complex Puppet code. It gets a little hairy on the command line when you're actually spelling out resources in line from the command line. So you'll see like simple includes and things like that with this syntax. The second one there, the Puppet Apply file.pp, you're actually just applying a manifest directly, and this is probably the most common way to use Puppet Apply. So a simple example, Puppet Apply site pp might be a way to invoke that. In the bottom one, we've got a Puppet Apply, and we're specifying a particular Hyra config. In this scenario, the site pp is actually the default manifest to be applied. So when you use this syntax, it's going to look for what's in your site pp in order to compile its catalog. This type of standalone architecture, it makes the most sense in cloud-like, microservice, kind of an ephemeral, throwaway environments that only exist for a short period of time. And that happens to be perfect for our current use case, building Docker images. So Puppet Apply with Docker. So with this configuration, we'll have a standard Docker file, but the bulk of the heavy lifting of configuration of the image will actually happen via Puppet. So a Docker image, it's a great use case, as I mentioned before, for the Puppet Apply model because of its ephemeral nature. There's no benefit to its active management. So within the Docker file, R10K is going to be used to aggregate, install the actual Puppet modules on the image. In the exercise in this lesson, the Puppet Apply command is actually invoked from the Docker file, as I mentioned. It's used to build the image via the command on the right side of this slide, Puppet Apply, specifying the module path there, the common etc Puppet modules, then specifying the Hyra config, which is also in the standard location, etc Puppet Hyra.yaml. Yeah, so Puppet Apply makes it easy to leverage Puppet code in building Docker images. Puppet-oriented shops, they can take advantage of the benefits of containerization and microservices while maintaining their configuration management standard practices. They can still use Puppet in this context. And oftentimes, the same Puppet code that they've been maintaining and using in more common traditional environments, they can still leverage that same code in building these containers as they containerize components in their architecture. In the upcoming demonstration, you'll see Hyra used as an ENC, as is commonly done. However, node classification isn't too much of an emphasis in this lesson because it's essentially a single node environment. SciPP is solely comprised of a Hyra include classes statement. The Hyra include is a function that will automatically include, in the Puppet sense, all of the classes specified in this case, a classes array in Hyra. So if I have an array defined in Hyra, and it's got Apache, an MOTD, an NTP, that will be the equivalent, this Hyra include function, it's the equivalent of saying include Apache, include MOTD, include NTP. There's also a lot of image-specific static config in Hyra, and we'll get a little more into that in the demonstration videos. And that about wraps up the discussion of Puppet architectures. Go ahead and mark this complete and move on to the next lesson. Thanks for taking the time.